He is assistant professor in Koç University in Electrical and Electronics Engineering departments. Moreover, he is the founding director of the Photonic Architectural Laboratories as well. Before yielding the floor to him, I'd like to make a small announcement about our privacy regulations. So since this seminar will be recorded and uploaded to YouTube, dear participants, if you do not want to appear on YouTube, we suggest you to not turn on your cameras. Thank you very much. Emir, Salih Hocam, the floor is yours.
Can everybody see the presentation?
Yes, we can.
Okay, all right. So welcome everybody. Again, thanks for having me. This is nice to see really interested undergraduates and also graduate students together in optics, as well as have you guys come together, hopefully at the end of this pandemic now. So to get you guys interested in research in this field, as well as potential developments, some of them recent, some of them over the last 5 to 10 years that I will talk about today, and hopefully give you a bit of perspective on what this research is, where it's going in the next 5 to 10 years, potentially, and some of the things that we're bringing in from an artificial intelligence perspective, to hopefully really bring it together in terms of some computational enhancements together with the silicon photonics, more conventional silicon photonics knowledge that has been built over the last 3-ish decades that the field has been really active. Okay. So if you would like to get in touch with me, right here is my lab's webpage. Photonic Architectural Laboratories. You can get in touch with me either via email, or if you go on there, you'll find a lot of information about what we do, some of our projects, our publications as well. Okay. So just looking at the audience, I thought it would be good to sort of talk about the general field of silicon photonics first, and then in the second half of the talk, talk more about some of the advancements that we've been enabling in this field. So you are already familiar with the electronics revolution that has happened over the last 50 to 70 years. That started with the invention of the transistor. That was at first a discrete bulky device that went on to the first integrated circuit that involved 2 integrated planar transistors. And then after about 10 years after that, the microprocessor, and then essentially yielding us today's modern technology with nodes that are sized below 14 nanometers these days, with billions of transistors and tens of billions of transistors in modern processors, with clock speeds that are now over 3 to 5 gigahertz. And this sort of revolution is very representative of what we will see in many fields in the future. That also includes photonics. I will talk more about that in the next half hour or so. You can see, following through that, the increase in the number of devices, that typically means the number of transistors that these digital circuits house, has doubled every 1.5 years or so. And that still continues with a couple of stalls here and there to this day. And you can see that a similar type of trend has also happened in the clock frequency of these devices. Now here, what I'm showing is the cutoff frequency for each one of these transistors. That's not exactly, of course, the same as the clock frequency of the whole processor, whole CPU, or the whole GPU, but it does give us an idea about the scaling trend that has been going on. in which for the past about 10 years or so, there's been a significant slowdown in the speeds that we can run these transistors and also these processors at, okay? Now, there are multiple reasons at play here, but two of them are really important. One of the reasons that actually gives rise to this stalling in the cutoff frequency or the clock frequency is material dependent. So there are material limitations as to making things smaller / faster, where at some point you are going to need a different design or a different material that you can design in a different way in order to enable these really fast speeds, really accurate and precise switching performance. Okay, that's number one. The other one is that there is a trade-off here in that if you run these devices really, really fast, you're also generating a lot of heat. So at some reasonable cost, you have to actually dissipate this heat. That's why if you ever built a computer by yourself, you know that you have to put on a heat sink on your fan. And if you have a graphics card or any extension cards, they have these very typically beefy heat spreaders on them with multiple fans. And running those actually comes at a cost. So even though you're generating a lot of heat, it's not free to remove that. You have to be able to remove it at some reasonable cost, okay? So those are two very typical reasons why you don't want to try to increase this cutoff frequency. And in fact, you can't actually increase this cutoff frequency too much more, okay? So I want to talk about these electronic circuits from the bottom up a little bit. These electronic circuits are made with silicon as our material of choice. And there are multiple reasons for that. Silicon is a very abundant semiconductor. Abundancy means that it's typically cheaply available, at least in comparison to other materials. The fact that it's a semiconductor means that we can tune its electrical properties in the ways that we want. And that gives us a lot of flexibility while still using one single material in order to essentially build devices that sort of do different things depending on how you configure each part of your device. Okay, and this is of course a very meticulous process. And at scale, there are only really a handful of really large companies around the world that do this sort of stuff. But just to give you an idea, these silicon wafers that are typically thinner than 1 millimeter come in very standard sizes, between a large dinner plate to something that you can very easily hold in your hand. And the electronics industry essentially builds pieces of devices, pieces of transistors, by literally carving out pieces of silicon out of these wafers at a quite a tiny scale. Okay. So any type of integrated industry wants to build on this existing manufacturing capability so that you don't have to develop your own manufacturing line and you can leverage the existing expertise in this field already, okay? So we do this in clean rooms, and the reason I'm putting this here is also a bit of a plug for our new clean room as well as our new research center. We will be doing a lot of this work in my own lab as a part of our new clean room effort. I know some of you will be familiar with this from other universities as well. And the reason I'm putting this here is not only to show you that this is where these things are fabricated, but also to show that it's really a very meticulous and very hard work to fabricate these devices well and to specifications. That will what I just said will come into play in a little bit when I talk about this design, fabricate, and test cycle. So when we build devices, that typically means you want to apply some sort of function to a signal, whether that's electronic or photonic signal. Okay? And very likely, you're using some sort of processing method that takes advantage of some sort of beam. This could be an electron beam here. I'm showing an example of an optical beam that essentially writes something on the back of what we used to call these optical storage media, where you might remember CDs. You probably do remember DVDs and Blu-rays, where the difference when you go from one level to the other is that you're writing with a shorter wavelength of light. That means you can focus it better. It can focus to a tighter spot, and it can differentiate between things that are closer to one another. So when you go to shorter wavelengths in processing these sort of wafers or optical storage media, you are able to create smaller devices. So you're able to create smaller transistors when you process with a shorter wavelength of light in the clean room. Same thing here, when you try and write optical media, you are able to write more onto a same size disk if you're using a shorter wavelength. For example, a modern Blu-ray disc, if any of you have still Blu-ray players at home or at your dorms, those use a blue colored laser, hence the name Blu-ray, okay? And you won't remember this. In fact, I also don't remember ever seeing one of these back in the day, but this is around the time I was born, actually. These are the types of devices that people used to build in data for operations such as you would see in data centers these days, at least, to separate different colors of light that arrive at some receiver node, for example. And these used to be hand-sized. If you look for them, you can actually get them on eBay, which is kind of an interesting souvenir. And because of the scaling, making things possible at shorter wavelengths and scaling the size of devices, our integration density, we're now able to do essentially from a centimeter scale, a shrink down to a micron scale, which is an order of 4 orders of magnitude scaling in length, which is an 8th order magnitude scaling in the device footprint of these things that we can create. I'm just showing an example here from a certain system where you can see a waveguide that sort of goes back and forth with multiple other waveguides bringing in light to those from the side, and then multiple electrical contacts that in this case control various electrical properties of the light, electrical properties of the waveguides that light passes through. And this is remarkable. So if you think of how far we've come in terms of being able to process things from these hand-sized devices to something that can now house many millions of photonic devices at the size of a chip that's as big as just a fingertip, that is a remarkable feat. And that's great because we'd like to leverage this, okay? We don't want to build in silicon photonics. We don't want to build our own new manufacturing capabilities. We'd like to leverage the existing capabilities that people have built over the years for electronics. And that just by itself places some restrictions on what types of devices we can build, but at the same time, it gives us the flexibility to really focus very well on the design of devices and have the fabrication be available to us with these really advanced tools, whether that's optical lithography, like I'm showing you here, or other things like electron beam lithography, like you may have heard of, and which are the two most common fabrication methods that people use these days. So just to give you some perspective, I've given you examples of sort of how these devices are built, whether those are electrical or optical on chip. Now I'd like to talk just briefly about how would we use these devices. So one of the really earliest applications of silicon photonics was to overcome overcome communication bottlenecks in these types of networks. If you've ever been to the computing cluster of your IT department, you'll see racks and racks of computers that are connected with these types of backends to either other local servers or also to the World Wide Web. And these are copper cables. These are what you'd use in order to connect an Ethernet port to your laptop, if you ever do that these days. And inside of those are copper wires. Those wires are way past their limits now. Essentially, being able to provide even 10 gigabits per second over long distances is really challenging because you can reliably do this either at a very short distance or at very low speeds. But if you try and do both at the same time, you are going to run into some difficulties. And there's also some difficulty with running a certain number of channels because if you think about it, for each channel, if you need a single wire, that's already a lot of wires when you want to carry a lot of signal. Of course, you can do some multiplexing onto these, but the amount that you can multiplex also has some limitations on it, depending on the capacity of these channels. So we really want to improve the bandwidth of these channels. So the information carrying capacity of these channels has to do with how much you can multiplex onto one channel, and that has some fundamental limits, which optics excels compared to these radio frequency or higher frequency or gigabit per second type speeds. The other issue is that when you try and run multiple chips or just a single electrical chip faster and faster, like I said before, you are inevitably creating some thermal output. If you look at a modern CPU, the vast majority of the part of the CPU that you see is actually the heat spreader. And there's a lot of engineering goes into designing that because that's such an important part of a processing unit that handles this thermal budget so that you can effectively cool it so that you don't have to start running things slower just because otherwise it doesn't run as expected, okay? If any of you are familiar with either high performance computing or also gaming computers these days, thermals are a huge issue. If you run your processors, whether that's CPU or GPU or really any other processor, above what's called a junction temperature, your transistors aren't going to function as properly. So what typically processors do is that they throttle back. If you want 100% workload and they sense that they're getting really hot, they will actually throttle back and works slower. The same thing, and this is not specific to just PCs, the same thing happens with mobile devices as well. Mobile phones, tablets, if you see that they're heating up, or if you actually, if you leave them out, maybe just in front of your car's windshield or anything like that, you'll see that they'll heat up, and there's some sort of thermal checks that the software of those devices do. If it gets too hot, it'll say you can't use your phone or tablet for a little bit. You have to wait. So that's some form of thermal throttling. Both of these issues, optics deals with fundamentally. That doesn't mean there's no bandwidth limitations or there's no thermal budget in a device that in an optical device. Of course there is. But compared to electronic devices, especially in communication and also somewhat in the computational disciplines, when you do these types of operations with optics, of course there are questions as to how fast you can do these, but fundamentally the types of operations that you can achieve with optical communications or also potentially with optical computation in the future, they can be much more efficient and much faster than their electrical counterparts. Okay. In fact, our internet right now, the fact that I'm talking to you, and the services that we're using, whether that's entertainment or communications or finance or anything like that, any information access that we have is thanks to this vast submarine cable network of fiber optics. The fact that you can access your email that's on a server maybe a few thousand kilometers away, or maybe closer than that these days, is because of the fact that there are physically cables laid down underneath the oceans that connect essentially this part of the world to all these other types, all these other parts of the world. And these cables are essentially fiber optic bundles. They're literally cylinders of glass tubes that you see in the center here. I'm not sure if you can see my cursor, but these are the fiber bundles themselves. Around them is just a lot of protective shielding. Okay, so the information runs in these channels, and because of fundamental reasons, as well as a lot of developments in the fiber technology, we can carry a lot more information a lot farther in these fibers than we can do on just copper wires. Okay. If any of you are curious, these types of wires will carry optical information about 100 kilometers before needing to be amplified again. So at about approximately every 100 kilometers or so, there's an amplifier in each one of these cable networks. Okay. And if you have questions about those, we can talk more about those amplifiers. But essentially, the fact that we are able to communicate information through these means that, just like the electronics industry, the photonics industry can undergo, and in fact is undergoing, a similar revolution where we're able to build these at a much smaller scale, with much smaller footprints, with much smaller power consumption, essentially miniaturizing everything so that we have optical processors, optical communication networks on a chip. Okay. Now, these optical communication networks essentially multiplex or combine different colors of light onto one fiber and impart information onto each one of those fibers. The way that's done is by putting them through what we call these filters, and there are many different ways to build these filters. Essentially separating these wavelengths onto individual modulators. These modulators convert electrical ones or zeros into optical ones or zeros. Very simply put, think of it as light on or light off, okay? And then we combine them together onto a single fiber and then transmit that, okay? This could be a fiber underneath the ocean that goes to another continent, okay? This could be a fiber recently that actually comes all the way to your apartment, as close as your front door of your apartment, actually, with some of these new fiber technologies. Okay. So there's fiber internets now, which is something you may have heard of. It is typically much faster, but it is very expensive. You physically have to have someone come and run a fiber through your street so that you can have access to it, okay? And when you receive it from this fiber, whether that's an ocean away or whether that's just from your local service provider that gets information from a local server, you receive this, you filter it again according to these colors, and you detect them on, here they're germanium detectors, but it really doesn't matter what the detector is. It essentially creates your electrical ones or zeros out of those optical ones or zeros that have been transmitted, okay? So sort of in this hybrid ecosystem, what we have are photonic signals that carry the information and electronic modulators and detectors that convert back and forth between electrical and optical data, okay? And there are many different subsystems that these are used for. So this hybrid system works really well, and this is sort of the current paradigm right now. Now, just to sort of bring this together for the first half of the talk here, silicon photonics is the field of combining these optical technologies, the fiber technologies that I've talked about, with the existing silicon fabrication capabilities that we have developed over the last 50 to 60 years to create devices that can leverage both optical and electronic capabilities together, okay? And this is possible. Many examples of this already exist, and there are many very innovative companies that build these types of devices these days, where you have full integrated circuits that have transmitters and receivers that can communicate either wirelessly or with fibers with other servers that can apply many types of different optical and electro-optical functions to different types of signals on chip that enable a lot of different applications, from autonomous vehicles to various other types of sensors, to micro displays, to memory, to CPU communication and other types of communication networks as well. So this really is a very important and also exciting field for not only what it enables right now, but the types of applications that it will enable in the future. And that's not just communications, like I said. There's a lot of healthcare in this, including diagnostics, including the point of care treatment, as well as various other types of health-related or sensors-related applications. Okay. So this is the general field of silicon photonics that we know today. Now, the silicon photonics revolution, I've already talked about this. This has started at first with a different material called indium phosphide because of various limitations in silicon. But silicon itself has fairly comfortably taken over. And here I'm just showing from a recent review paper by by John Bowers, this group at UCSB, where they have actually scaled, they've actually shown how the scale continues to this day, where we are able to put in more and more components onto every single photonic integrated circuit or photonic integrated chip, increasing our integration density and at the same time overcoming these various thermal as well as communication bottleneck issues. The similar trend, as you can see, in electronics has already appeared in the photonics industry, and we are lucky that at least I feel that me and my group is lucky that we're able to leverage this sort of fabrication technology and contribute to these really interesting devices and systems that enable next generation communication or diagnostic applications. So I want to talk about a couple of the important advantages of using silicon, and some of which is also the reason why I like using silicon myself. The first one is something that I think everyone can vouch for, is the really tremendous integration density that you can achieve with a silicon dioxide platform. And we use this, of course, every day in our research. The reason why we can pack optical devices so close together on chip is that when you put silicon and its native oxide, silicon dioxide, next to one another, the refractive index between those two is actually very different. The refractive index of silicon is about 3.5, where the refractive index of silicon dioxide is about 1.5. So those are very, very different. That means if you try and confine light to a narrow piece of silicon and route it to a different location on chip, you're going to find that that's very easy, in fact. Okay, that's why we can do these really tight bends without losing essentially a minimal amount of light, so that your devices can work really efficiently with a very compact footprint. Okay. The second effect is the electro-optic and thermo-optic effects. The first one I'm showing is the electro-optic effect. This is essentially the fact that silicon is a semiconductor. We can control various properties of silicon with electrical signals, which means you can actually control what silicon does to optical signals using electrical signals. And that is, in fact, one of a lot of people's favorite things about silicon, is that not only we have access to all this mature fabrication platform that's been developed, but part of the reason why silicon has been used so extensively is that it is relatively, at least these days, easy to control these types of electrical properties of that element. The next one that I like quite a lot myself happens to be the thermo-optic effects in silicon. So this is kind of a double-edged sword in that silicon actually is a very thermo-optically active material. That means temperature tends to have a comparatively large effect on silicon than a lot of other materials. That means silicon's refractive index changes a lot with temperature. That's what it means to have a high thermo-optic coefficient. And actually, this is great because you can build devices that can either do something different at different temperatures or just sense that change in temperature, which gives you a whole slew of new capabilities for different types of sensors. At the same time, this does create some difficulty if you have a device that does need to perform up to spec at a whole lot of different temperatures. So sometimes you don't want the device to shift its operating wavelength at a different temperature. And there are various methods that you can design your devices in order to enable that. And that, in fact, is one of the research areas that we have focused on in the past, and we will also be focusing on in the near future. And lastly, I think this is a bit, this is not as emphasized, but I think this is really one of my favorite reasons to work with this kind of platform, is that silicon is a very well-known material. And that's partly due to the fact that the whole electronics industry has been built around it. More than that, the theory of electromagnetics has been developed over 100 years ago, and we still, to this day, use that same theoretical understanding to model our devices. And that means that if you actually design properly, and that does mean a lot of different things, that means doing simulations very carefully, very accurately, and in a way that does represent reality. It's actually not extremely difficult to get experiments that are matching your design. I'm just showing an example here, and there are many that you can show with similar specs, that your design, if you do it right, can match your experiments very, very well, extremely well. Okay. And that's one of my favorite reasons to do silicon research, as well as research in photonics in general, is that there's a lot of really, really capable simulation and design tools that we can leverage with the right expertise, so that our experiments will match essentially within a bound perfectly well to those designs. So this cycle goes back and forth between design, fabricate, and test. And like I've mentioned before, the way we do design is through simulations, and there are very different ways of doing these simulations. The way we fabricate, you can do them locally if you have a local clean room at your research institution, or more often it's a CMOS foundry, which has built expertise over decades of research into building these devices. But what's nice about using a foundry is that you can focus on the design and have the fabrication be done by the experts in the fabrication field. And then testing, there's various ways that this can be done. It's very typical that this type of testing, after you fabricate your devices, you do in your own research lab, which is currently what we do, but there are also quite a few testing companies that are popping up around the world that will do this sort of testing for you as well. And that's a relatively quickly learnable skill, although it takes a lot of practice to become an expert, just like everything else. Now, the thing I want to mention here is that fabrication is extremely expensive, and I can't I can't overstate this. I think there was a couple of years ago, and I think this is just around the time I was finishing my PhD, I heard a fact, and I think I did a very quick calculation just to sort of verify that if you were to build a medium-scale CMOS foundry where you replaced all the equipment with gold instead by weight. So if you had a 100 kilo equipment, you replaced it with 100 kilo of gold. What I heard was that the equipment was more expensive than gold. And then I'm fairly certain that still holds true to this day. So if you were to, in fact, the equipment gets probably way more expensive, much faster than the gold appreciates in value. This building a CMOS foundry, running it is extremely expensive. It's a huge task. So if you can have your designs work the first time, that's always the best, because it takes not only a lot of funds to fabricate devices properly, but also it takes a lot of time to do it well, okay? So if you focus on simulation, and that does mean a lot of different things, lots of information that you have to bring together from different disciplines, such as electromagnetics, mathematics, physics, electrical engineering, you are better off in general than trying to fabricate over and over again without having done proper simulations on your designs, okay? And that's why my lab currently focuses on mainly simulation and research, simulation and design and test tasks. And currently we are outsourcing our fabrication with efforts to start it in the very near future locally. Okay. So let me give you a couple of examples of our last bit of work that we've been doing. Here I have an example of silicon photonics device library, which means a lot of things that have been built over the years. That's various types of waveguides that carry light from one point to another. Those are various types of filters. Either they filter by wavelength or other spatial properties of light. And these are some interesting types of couplers that couple light on and off chip vertically or horizontally from the edge of the chip, and so on and so forth. And these have all been built, but there's a lot of similarity in these seemingly very different devices, in that if you look at them, they're always very structural. And that's not a bad thing, but it does mean that someone has to actually, if you look at this phase shifter device, the middle one in the top row, someone has to actually think about what this length should be, what the bending radius here has to be, how many fingers to include on this antenna, and what the gap between these two waveguides have to be, and so on and so forth. So all of these decisions actually have a meaning. And you learn to make those decisions by running a lot of simulations and really learning what's behind those results from various mathematical descriptions, okay? Now, the device that I think is appropriate for a very general audience like this to talk about is one of the most fundamental devices in integrated photonics. It's called a directional coupler. This is a two inputs, two outputs device example that I have here. The idea is that you have an input, let's say on the top port here. You come in here into the second region, and some of the light that you have input to the top port couples to the other waveguide on the bottom. And the amount of coupling you get, of course, depends on the length of that section, the gap between those waveguides, the widths of those waveguides, what wavelength your input's at, and so on. And some of it remains on that same waveguide, okay? So if you, for example, if you design this properly, you can get it to work as a splitter that splits incoming light evenly between the top and the bottom port. So you have one coming in, and then at the end, you have 50% and 50% going out in terms of, let's say, power, okay? What typically this device does is only possible for a very narrow wavelength range, okay? So you design this at certain wavelength, let's say 1.5 microns of wavelength, and it works around 50-50 as a 50-50 splitter, so even splitting between the two outputs. But what happens is that if you change your wavelength, it doesn't do what you want anymore. For example, if you look at this here, it says that if you go to a longer wavelength, suddenly the splitting ratio, even though you've changed wavelength very little, the splitting ratio has become, for example, 75% to 25%. Okay, so that's an undesirable effect. You normally do not want this because it reduces your yield. You don't want to be able to, in a device that you're building to handle a wide range of wavelengths, you don't want this kind of effect, and there are various ways to design around that. One way that people have specifically examined in the past is using an unbalanced interferometer architecture. Okay, interferometer is essentially a glorified version of a directional coupler, where you're interfering one signal with another signal in a directional coupler that's sort of specially designed, okay, in this example. Turns out you can do very interesting things with that kind of device. And here I'm just showing results from a different group in this field, the results that are fairly recent, 5 to 10 years old, if you can call that recent. Which show that you can actually design this properly so that the 50-50 splitting ratios actually maintained very, very precisely within from 1.5 to 1.6 micron of wavelength, okay? And it turns out that there's a lot of mathematical optimization behind this. So, as you increase the number of variables you can control, you slowly start losing the physical insight, which is not great, but that is in fact what does happen. If you have hundreds and hundreds of variables that you can control, which wasn't the case in this work, but if you increase those numbers of variable, at some point you are slowly starting to lose what each one of those variables does to your final result. Right? You can say the same thing about a lot of different problems in engineering or physics. So in this case, if you're just sort of tuning a couple of different parameters, in this case like this, this phase difference at the two arms between the two directional couplers, that's sort of one nice thing that you can try and optimize to get a result that works really well. And that could be, in this case, like they did, a 50-50 splitter. Okay. But you can do a lot more. And this is one of the things that we have examined recently. We can build this phase control section, let's call it, because it controls the phase of the light that travels inside of this range in a very custom way. You can, for instance, think of the fact that this section you can model with a couple of different widths and then just trapezoids that connect those two widths together, okay, section by section. Of course, this is a very simple design. You can do all sorts of continuous descriptions here too, but the idea here is that you can control the phase in a way that you can't really try and do one by one, okay? If you imagine there's about 5 or 10 of these widths here, and then there's another 5 or 10 down here, it's becoming really difficult to try and set each one of them by hand, okay? And that's where artificial intelligence comes into this work. And that could mean a lot of things. It could mean that you do, really very simply, do a brute search of all possibilities and find the set of widths that work the best, okay? That is an artificially intelligent design paradigm called brute search. Of course, it's not a very intelligent artificial intelligence, but it does work. It's very slow because you have to try a lot of different things, but it is the simplest artificial intelligence. You try a bunch of things, choose the best one that comes out of that. You can't do that as a designer your simulator has to do that for you. So this, although it's very non-intelligent, it's already able to produce results that are better than what you can do just by hand, right? And now imagine what we can do once we look at using more intelligent decision mechanisms. Let me skip over this and show you what kind of results that we can get with this. So just with one phase section variable, let's call that. That's just one different width than what we had before. We can optimize this to this black line here, where the target was this blue line. Okay, we want it to be 50% across the whole wavelength range. With just one variable, we can do this. Okay. So it's, as you can see, it's much closer to the ideal design. That's something that just goes through this 50% line. But as you can see, there's a lot of room for improvement. Now we can increase the number of variables here, and at the same time use more sophisticated search methods. And we can talk more about those if you like too, but here my point being that these more capable descriptions of the device that you can build will most likely give you better results if you know how to search in that space. Okay, so as you can see, this is even closer to the ideal response, but there's still a lot more you can do, right? You can include more weights or more widths in this case. So this is what we had with just one n equals 1. And here I'm showing you that as you increase the number of widths in that section, you can actually get a lot better to, and a lot closer to the 50% line that's your desired response for this device. This is a 50-50 splitter from 1.4 to 1.6 microns, but as you can guess, you can build many other types of devices with this type of artificially intelligent design paradigm. But of course, what I'm showing here is a very simple example of that. You can do things that are really much more sophisticated. But I'd like this to just sort of serve as an example of what type of artificial intelligence we can use, and that typically means sort of clever searching algorithms within a predefined design space that gives us devices that can yield functionalities that are either previously very tough to design or actually impossible to design. This happens to be one that is possible to design, but if you were to change the specifications a little bit, it becomes an equivalently difficult to design problem when you want to do it the conventional way. Here, it's also an equivalently difficult design problem, but that difficulty is really just optimizing these variables for a different target function. So we have a lot of capability there that simply does not exist when you want to go the conventional route. Okay. And like I said, you can either, for those of you who are familiar in the audience, you can use heuristic methods or more analytical approaches that most machine learning or deep neural network scientists do these days, which we are currently also using. Okay, so I'll summarize and end here. I've given you a brief overview of the silicon photonics industry, which is the ecosystem of systems on chip in the optical realm. And I've sort of talked about the electronics revolution that has happened in the 20th century and how the photonics industry is also going through that same revolution in the 21st century. I'm sure many of you who are interested in this field will, when you start looking, you'll find many interesting companies that do really amazing work in this field, whether that is fabricating devices, creating these actual devices, or on the other side of the medallion, doing this for what's called fabless photonics, where you design your device, have the fab be done by other experts who have decades of experience in this field, in many types of applications. And that could be communications, which is one of the first applications of silicon photonics that people have used. But it could be a whole lot of other things, whether that is autonomously driving cars or other vehicles, whether that's microdisplays or biomedical diagnosis or treatment applications, or GPS, timing, scientific discovery, and a whole lot beyond that as well. Okay, so with that, I'll finish here. Like I said, I'm happy if you have questions or if you would like to get some experience working in this field to talk to you. You can reach me either by email here, and you might have to email me a few times depending on how busy that week is, or also go on our website to just discover more about our research.
Thank you very much for the presentation. So if you have any questions, we can write to the chat, or we can open up the microphone.
Okay, I can ask one. I'm going to ask about the wavelength separation in fibers. So, for example, 1.55 micron, of course, the minimum loss wavelength, but for different wavelength, there must be a separation. So, what is the minimum separation? Not all of them is 1.55 micron, of course, but must be different, I guess.
Yes, of course. So if I understand the question, what you're asking is how different must the wavelengths be, or maybe how different can the wavelengths be in a communication network?
How different can be? Yes.
So there's no fundamental limit to what the separation between these wavelengths have to be. As long as you can filter them without having the filters shift spectrally too much, they can be as close, as arbitrarily close as possible. But of course, that's the utopia, right? There are standards, so-called ITU standards, that determine how close or far apart these wavelengths have to be. And in those standards, very typically used these days, in the 1550 nanometer range, or the C-band, is called DWDM, Dense Wavelength Division Multiplexing Networks. And it turns out that there are spaces within those dense WDM specifications that say each one of these wavelengths have to be between this and that, where the spacing is either 25 gigahertz or typically a variation of that depending on the standard that the year was published. So 25 gigahertz is actually a very, very short wavelength range. 125 gigahertz is about 1 nanometer at this wavelength. 25 gigahertz is actually much narrower than that. You can look up the most recent specs, but that typically tends to be what's the dense WDM happens to be currently. There's also coarse WDM that's used for other types of communication networks, and that's much coarser. The spacing for that typically happens to be around 20 nanometers, which is much more wider. It's much wider than the dense networks. Okay. But the interesting thing is that these standards get better and better every decade. So at some point, it's possible that our devices are so good that the spacing between each one of these happens to be just 1 gigahertz. And we can, instead of multiplexing 64 channels, we can now multiplex 64 squared channels onto the same fiber. And if you look at the trend, that certainly is possible over the next couple of decades.
All right, thank you.
I want to ask something about fabrication. You said you use trapezoids for phases, let's say. Do you fabricate that shape on the fiber yourself, or do you use some kind of like a small tool or something?
So let me explain how fabrication of something like this would be done. You can build here any shape. It can be a trapezoid. It can be a continuous function where the derivative, where it doesn't have corners, the derivative is continuous, for example. It doesn't matter as long as it's within some fairly relaxed fabrication rules, okay? You can't have corners that are really tight. But we can build with those specifications in mind. But the way you fabricate this is not really a manual process. You have a file that defines this sort of drawing. We typically call that a mask, but it's essentially a stencil where you mark the boundaries of these waveguides. And then either when you're using electron beam or optical lithography, that mask is transferred to a photosensitive layer. You shine the beam, essentially, either at once or locally by scanning, on these regions where you defined your mask and in between them, sort of marking these regions, okay? That means that the substrate, the silicon substrate, and the photosensitive layer that has been deposited on top of it is now been marked in these regions with some sort of beam, either electron beam or optics, okay? After that, that goes through a process where you remove those parts, or exactly the opposite parts of that photosensitive layer, okay? So that you have photosensitive layer only on the parts that you want to keep or get rid of, depending on the type of material. And then you etch, which means carve. You literally carve out the material, okay? So when you do that, you are carving out pieces of this material in this green region, leaving these parts intact, okay? Essentially, when you wash the whole thing afterwards, the parts that are protected by that photosensitive layer are left here, the blue parts, and you've etched down, you've carved down on these green parts. So you have these parts raised now, okay? That's how you create these waveguides. These aren't in fiber. Maybe that didn't come through when I was talking about this, but these aren't in fiber. These are planar waveguides that are on chip, okay, in silicon substrates.
Okay, thank you, Hocam. I understand.
Sure.
Hocam, I was going to ask something about the amplifiers that you talked about optical fiber optic cables under the oceans. So when the signal is amplified, does it does the quality degrade?
So very good question. Yes, amplifiers and lasers, very similar devices. They are a huge piece of research in this field, and in fact, a lot of research has been done in those amplifiers over the last 30 to even a longer amount of years. The degradation of the signal when it goes through an amplifier is a major concern. Not currently, but it used to be that the noise figure is how you typically quantify these amplifiers, is used as a means to look at the quality of the signal before the amplifier and versus after the amplifier. And that can be a concern if you have the wrong type of amplifier. But these days, I don't believe it's a hugely active concern for these really long haul networks is what those are called. Thousands of kilometers long networks, ultra long haul networks. You have an amplifier that works reasonably well within its specifications, and its specification says you need to put this amplifier every 100 kilometers. If you delay it to 500 kilometers, of course, the signal will have been lost more by the time it reaches the amplifier. So you'll be amplifying a lot of noise. So you don't do that. Of course, working with an amplifier that has a that can provide a cleaner signal could mean that you could potentially extend the 100-kilometer range to potentially longer ranges, to 500 or 1,000 kilometers. But currently, I don't think that it is such an actively major concern, the quality of the amplifier, that is. If you want to look into learning about that, you would be reading about erbium-doped fiber amplifiers and noise figures of those amplifiers. Those are the two things you would be looking up. They tend to be, I would say, very good, but they are at least very good for this application specs.
Okay, thank you.
I should clarify one more thing. If you are thinking amplifiers being electrical, they're not. So you don't receive the optical signals, convert to electrical domain, amplify, and then convert back to optical domain. That problem has been solved by amplifying them in the optical domain. So light in, light out. No electrical components, and well, at least no information transduction to the electrical domain. Okay, information stays optical.
Okay, thank you. And when you talked about the design process and the simulation process, I mean, what kind of steps do you go through during your design? Or, for example, which software do you use?
Yeah, very practical questions. I'm glad that you asked. The types of software that we use are essentially electromagnetic simulators. Okay, some of them we build, some of them we use available ones. Most of the programs that we run these days, at least the ones that we have the source code for, are based in Python, but that doesn't define anything about the field itself. It's just that these days Python has become the standard for a lot of different types of work that people do. And the students who are working in my lab right now, I would say about more than half of them are building / using simulation tools in Python. Okay, so if you're looking into going into this work, or really anything in the engineering field these days, understanding basic Python is a must, but it's not very difficult. If you're familiar with anything else, understanding a similar language like Python is very, it's a syntactical change. It's 1 to 2 weeks of practice, I would say. The actual simulation methods we use are more varied. They can be finite difference type simulations, so finite difference time domain or finite difference frequency domain. That tends to be one of our favorites these days, because we can build some exceptionally fast simulators. We have some work going on building those simulators ourselves, as well as using and building efficient simulators that are simpler in nature. For example, a device like this only needs a simulator that does 2x2 matrix multiplication a few times. You can imagine that that's a task that's extremely fast. And one of the purposes, if you do more work in this field, you'll find is that the faster you can go through doing these simulations, the faster you can iterate and the faster you can design these devices. So we're spending a bunch of effort on building these devices in a way that they can be simulated really fast. And also a bunch of additional effort on building devices, building simulators that can run these much faster than currently available. Does that answer your question, or did you have any follow-up questions to that?
Yeah, it answered my question. Thank you. Any other questions?
Yeah, maybe extend that topic. Is there any reason to use finite difference methods, or sometimes do you need finite element methods for some reason?
So finite elements can be used, and we have nothing against it. Finite difference just seems to have become an industry standard that a lot of people understand really well, and we have collaborations that have been built on understanding and building finite difference mechanisms that tend to scale well as well. But we have nothing against finite element. It's just that finite difference has been working really well for us, especially in the frequency domain applications, that we are building finite difference methods that already sort of leverage existing libraries, let's say. There's a lot of linear system solving libraries that we don't have to rebuild, that you can repurpose for finite difference. There's a lot of other really, let's say, really cool matrix manipulation techniques that we leverage these days that tend to work really well if you have a finite difference type of discretization. There's no reason you couldn't do very similar and exciting things in finite element. It's just that finite difference just happens to be the choice of a lot of different research groups as well as ours these days.
Okay, thank you.
I guess there are no other questions. Hocam, thank you very much for accepting our invitation and giving this informative seminar. And we hope that we can see you also in campus face-to-face after the pandemic period. Thank you very much for the participators also to come and join us. And I will leave the contact information of the student chapter in the chat box. So if any one of the participants wants to contact us, this is our contact number. Thank you very much again to all of you, and have a good evening.
Thank you again for inviting me. It was really nice to share this research with all of you guys. I hope you come away at least impressed with the field. And let me know if you'd like to learn more about this field, and also if you'd like to do research in this field. And best of luck to all of you guys through your studies as well as your careers.
Thank you very much, Hocam.
All right. Have a good evening, everyone.